NPTEL lecture on earthquake resistant design of foundations. This is lecture number 33 for earthquake resistant design of foundations, and we are at 5th module of this course, which is on soil structure interaction. In today's lecture, we are going to talk about SGM, that is strong ground motion and wave propagation. So as discussed earlier, let's see that 5th module, that is SSI for deep foundations, and within this module, these are the chapters which we have already discussed, 2 chapters. First is introduction to soil interaction. Then in the second lecture, we talk about effects of soil structure interaction. So this is the 3rd lecture which is related to soil structure interaction. And today we are going to talk about strong ground motion, that is SGM, and wave propagation. And both of these strong ground motion and wave propagation, they are very much relevant to soil structure interaction, because the understanding of strong ground motion and wave propagation will help to understand the soil structure interaction, and the SSI is very important for earthquake resistant design of structures, as we discussed in the last lectures. So continue with that. Now we have today's lectures in 2 parts. One is strong ground motion and another is wave propagation. So let's talk about what is strong ground motion. Actually, you know that Mother Earth, when we talk about Mother Earth, it keeps vibrating and continuously vibrates. Okay, so vibration of the Earth could be, when we talk about let's say its period or natural frequency of excitation. So the period of the vibration could be range between starting from milliseconds to in days. It could be very large or it could be very small. Similarly, amplitude of the vibration could vary from nanometers to meters, and that is accordingly that magnitude of earthquake keep varying. Then microseismic activity, which is, let's say, weak vibrations, they are for greater importance to seismologists, but they are not so important for engineers. When we talk about strong ground motion, they are very important for earthquake engineers, and we need to find the quantitative ways of describing strong ground motion. Continue with that. So the ground motion due to an earthquake in general is very complicated. It is not easy. However, it could be represented by 3 components of translation and 3 components of rotation, which are usually neglected. Most commonly, 3 translation components such as north-south, east-west, and vertical are measured, and typical record of strong ground motion contain a lot of information. For example, 3 components of Bhuj earthquake recorded at Ahmedabad are given in the slides. So this is one of the components of Bhuj earthquake recorded at Passport Office of Ahmedabad. So what you could see, this component is called NE component, or sometimes it is also given from the north-south, one of the horizontal components. So that means this component is between this angle it is making with the north is 78 degree, and it is between north and east direction quadrant. So what you could see here, that this is basically acceleration time history. So on y-axis acceleration is given, which is in terms of g, and on x-axis time is given in seconds. So what you could see, that this is varying initially for few seconds acceleration is very small, but then it keep increasing, and you got the maximum value, which is called normally PGA, that is P ground acceleration, which is in this case about 0.10 g. This is the maximum. It appears to be maximum value here. This was the northeast component. Another component for horizontal direction, that is lateral component or transverse component, that is N 12 degree west. That means the previous one and this one, there will be 90 degree angle. They will be perpendicular to each other, but still both will be horizontal. In this case, you could see that is still, again, you have acceleration time history, and the peak is less than 0.1. So out of these 2 components, horizontal component, longitudinal component will be governing here because it has the higher value. Then the third one, that is called vertical component. Again, you could see for vertical component, again, this value of acceleration, peak acceleration is further smaller. So these were the 3 components of Bhuj earthquake, which are represented by the acceleration time. But in each of the component, let's say in the longitudinal component, what you could see here, that with the time this is keep changing. That means you have so many rise and troughs. It is increasing and decreasing. Okay, it is happening continuously. And if you want to use this the time history, then we need to do analysis at each interval of time, whatever interval of time you select, and it will require a lot of calculation. So to simplify that, what has been done, that in a strong ground motion, it is not necessary to reproduce each time history exactly to describe the ground motion adequately for engineering purposes. However, the characteristics of the ground motion that are of engineering significance needed to be described, and the number of ground motion parameters that reflect those characteristics needed to be identified. What is required? We want to have the parameters which can describe the characteristics of the ground motions, and these are normally represented by three parameters. One is called amplitude, frequency content, and duration of the motion. So amplitude of strong ground motions are represented by what is called, usually it is described by PGA, or it is called peak ground acceleration. Then frequency contents of the motion is normally described by what is called the Fourier spectra, and duration of the motions is usually in seconds. So naturally, higher the amplitude, higher is expected to be PGA, and higher the magnitude. Frequency contents, if frequency content is such that of your strong ground motion, that its predominant frequency is very close to the natural frequency of your system, your building or structure, then damage will be higher. Then you have duration of the motion. Higher the duration of the motion, naturally it is expected that higher will be the damage. So rather than using complete time history, these three parameters, and naturally the amplitude is the that most of the time PGA is very much influencing parameters. Its influence is larger than others. So, and then you have frequency content. So frequency content influence will be higher when you are going near to the natural frequency of the system. Okay, so using these three parameters, we can characterize the earthquake motion. So this was regarding SGM. Now coming to the second part of today's lecture, that is on wave propagation. It is understood that how the waves travels in a medium. So when we talk about wave propagation, we can compare that there is a what is earthquake. Earthquake is nothing but basically elastic waves in which the energy is released. So earthquake can be characterized as a release of energy occurs, and it is due to wave propagation only. So generation of waves in continuous medium like soil or Mother Earth due to disturbance in the medium are analogous to the waves which is created when a pebble is dropped in a pond. So when you drop a stone inside a water pond, then what will happen? The waves will generate. So this is similar to that, the similar disturbance is caused by the elastic waves or earthquake wave. An earthquake produces motion of the ground by the seepage of a stress wave that originate from the rupture of the stress earth mass. Waves may also be generated both at the surface and within the earth by man-made vibrations. Wave velocity depend upon the elastic properties of the medium through which they travel. So this is the last and is very important to know that velocities of the wave will depend on the elastic properties of the medium. So that means if we know the wave velocities, then we can characterize the properties of the medium, or it is other way also. If you know the elastic properties of the medium, then you can determine the wave velocity also. So continue with that. When we talk about wave propagation theories, normally there are three types of theories. One is called one-dimensional wave propagation in an elastic rod. That means it is very simple to understand. Here it is assumed that wave propagation is taking place in one dimension only, though it is very ideal case, but it is easy to understand, and it will provide you concept. Then you have three-dimensional wave propagation in elastic infinite medium. Okay, so because the earth can be considered inside the earth elastic infinite medium. But when you come on the surface of the Earth, then it is a semi-infinite elastic half space. So as we discussed in the last lecture, that is 32 lecture, that what is half space? Half space is basically semi-infinite medium. So the last one is the most realistic case, and we are going to discuss these three one by one. So let's talk about first one, that is one-dimensional wave propagation in an elastic medium. So here a rod is given in this figure. You could see x direction, dx is a small element, and at a distance x from the origin, the u is, let's say, the displacement or response in x direction. What is the, if you consider a small element with length dx, then on both ends, one end sigma x is acting, on another end sigma x plus delta sigma x delta x dx is acting. So that means there is this element is subjected to an additional stress in the side delta sigma x delta x. Okay, and this additional stress will create a force, and this force can be equated from the what is called from the Newton's second law, that is the force is mass multiplied by acceleration. Del E square u by del T square will give you acceleration, and if you multiply by rho, it will give the force per unit volume, which can be equated del sigma over del x, and sigma x is nothing but E multiplied by strain, where strain is del u by del x. So if you substitute E into strain, then we end up in this result. And finally, this relationship give you VR square equal to, where VR square is nothing but E by rho. What is E? E is Young's modulus of the medium, and rho is mass density. So this means the wave velocity inside this rod can be find out for 1D case as a square root of E by rho. Okay, so it is where E is Young's modulus and rho is mass density. So as you know that there is not much change in the mass density, but there is a large variation in Young's modulus. So the wave velocity or velocity inside the rod VR will depend very much on Young's modulus. Okay, so this was the case for 1D wave propagation. Now when we talk about in real scenario, three-dimensional wave propagation in an elastic medium, it is not simple like a one-dimensional case, but at the same time, what is done in this case? First of all, it is assumed that the infinite medium through which waves propagate is homogeneous and isotropic. Then 3D equations of motion of an elastic solid are expressed in terms of displacement. So what is done? You have three equations of which is called equation of motions, and in these equations, this whatever stress and strain displacements, what you do, you try to represent them in terms of displacement. And how you can do that? You need to pull the stress-strain relationship and then strain displacement relationship. And finally, manipulations of equations are done, and you get this solution of this equation, where epsilon v is nothing but volumetric strain, which is epsilon x, epsilon y plus epsilon z. That is the sum of normal strains in all three directions. What is Vc here? Vc is called the velocity of compression wave, and Vc square is given by this relation, where this is lambda plus 2 mu divided by rho, and lambda and mu are nothing but they are called Lamè's constants. Okay, lambda and mu are Lamè's constants, and both of lambda and mu can be represented by as a function of E and Poisson's ratio. So when you substitute lambda and mu in terms of E and Poisson's ratio, finally you end up in this relation. And in this relation, all quantities except rho is nothing but K, where capital K is bulk modulus. So if you divide bulk modulus by rho, then it will give you Vc square, that is the velocity of compression wave in the rod. Now, when mu equal to 0, let's say if I put in this equation mu equal to 0, what will happen? You will get E by rho. That means Vc square will be same as E by Vr square. So we can deduce the result that for mu equal to 0, Vc square is equal to nothing but E by rho. That is Vc is equal to the velocity of compression wave in rod. However, when mu is greater than 0, which is the realistic case, in that case, Vc will be greater than Vr. Let's say for a typical case, when Vc will be mu is 0.5, in that case, Vc will be approach to infinity. Okay, so that means the value of when the Poisson's ratio changes, then the rate Vc will be keep going on greater than Vr. Okay. Then the other solutions of the equations which lead to shear wave velocity of the propagation is given by Vs square equal to mu by rho, where mu is again what is called shear modulus, which can be represented E divided by twice 1 plus mu, and rho is mass density. So when the waves are traveling in 3D medium, then you have two types of waves. One is called compression wave. Its wave velocity is represented by Vc, and another is called shear wave, and its velocity is represented by Vs. So thus both velocity Vc and Vs are represented in terms of E, mu and rho using these two equations, this Vc square and this Vs square. Now the ratio of Vc and Vs is given by this relation. One thing I will like to emphasize here, Vc is many times represented as a Vp. So Vc is same as a Vp. Let me pull here. So Vc is many times written as same as Vp, where Vp is called P wave velocity. Okay. So here, because it is a compression wave, so we have used notation subscript P, but both are the same thing. So continue with that. Now this ratio Vc by Vs is given by this relation. You could see when mu equal to 0, this for mu equal to 0, this ratio comes out to be square root 2. So that means for any case, the Vc will be at least 1.41 times Vs. Okay, so minimum value of Vc by Vs comes out to be root 2, and when the value of Poisson's ratio increases, it will increase exponentially. Okay, and you could see when it increases, especially when mu equal to 0.5, then this becomes infinity. So these things we will discuss again. So the minimum ratio is Vc or Vs is square root 2. Continue with this. Now when we talk about 3D wave propagation in an elastic infinite medium, we can summarize the results like this. An infinite elastic medium can sustain two kinds of waves. One is called compression wave, and its velocity is Vc, and it is also called primary wave, P wave, or irrotational wave. Then you have shear wave with velocity Vs, and it is also called secondary wave, S wave, distortional wave, and voluminous wave. These two waves, which represent different types of body motions, travel at different velocities, and it may be noted that the particle motion, which is associated with the compression wave in the rod, and that in the infinite medium is the same, but the wave propagation velocities are different. So in one case it is Vr, wave velocity, in case another Vc, but the particle motion is same in both the cases, whether it is in the traveling inside the rod or in elastic medium. So continue with that. So what you have, we already proved that since Vc is greater than Vr, and they could be equal when the Poisson's ratio is 0, the compression waves travels faster in the infinite medium than in a rod. So both are compression of wave, but their wave velocity are different. In elastic medium, they will travel at a higher speed compared to in the rod. The second type of motion, which is S wave, propagate at the same velocity in both the medium, whether it is in the rod or you have in the case of elastic medium. Now the table which is given here, which is coming from the literature, this table gives you the typical velocity, wave velocity for compression and shear for different materials. And as you may be aware that these different materials, different types of soils, there is a large variation in the Poisson's ratio. For example, the Poisson's ratio is very high for the clay compared to the sand. So as a result, the difference between Vc and Vs will be the large for the clay, but as you go higher, for example, gravels, and then this difference, or grain sand, this difference will decrease. So this mass density given here, and here for the clay it is Vc and Vs is about 10 times, but the minimum, if you would see, the difference is about 3 times here. So in any case, the difference will be more than root 2, that is 1.41. That is, it cannot be less than root 2 in any case. So you could see 3 times, almost 3 times difference here, and so on. Here the difference is less than 2 times in dense sand and gravels, 480 and 250. So that means it is okay. So these are the values of Vc, and this is Vc is same as mentioned Vp, which is used for the P wave velocity. and these are the typical values only, representative values only. However, these values should be find out from doing that test. Normally what is done, the shear velocity are found using some experiments, and then assuming value of Poisson's ratio for given material, then Vc and Vs can be determined from this relation. Okay, continue that. Now, so far what we have discussed wave propagation in elastic three-dimensional case, but in real Earth case, because you have a free surface, so rather than saying it a infinite medium, as we discussed in the form of half space, it is a semi-infinite medium. If you recall in the last lecture, half space was like this. This was the half space was represented like this. So you have here going to infinity in all three directions, but you have on the top you have free surface. Okay, so here what this figure is showing, motion induced by a typical plane wave that propagates in the x direction. Wave motion you could see are changing, that is there is motion is in the particle motion is in x direction, and this particle motion is varying along the z direction. However, these wave fronts are same along the y direction, so there is no change in the y direction. So this for this case, for semi-infinite elastic half space, in practice the solution for wave propagation in infinite elastic body have little significance. Why? Since foundations are supported on the soil, the boundary conditions are those of a semi-infinite half space, not as a three-dimensional case. Therefore, it is assumed that medium is again here it is assumed like in 3D case that medium is homogeneous, isotropic and elastic. And for this elastic infinite medium, it was found that there are two types of body waves. One is the compression wave and shear wave. But when you consider elastic half space, the another third types of wave arises, and this is called the surface wave, and one of the surface wave is the relief wave. And the motion of a relief wave is confined to a zone near to the boundary of the half space. Actually, let me put like this. You know that when we talk about earthquake waves, if you may have some background about that, there are two types of waves. One is called body wave, another is called surface wave. So P wave and S wave are the body wave, while relief wave is the surface wave. Surface waves get generated when the body waves comes in contact with the surface, that is on the ground surface, then the surface waves get generated. Now let's discuss what is the ratio of the wave velocities, different wave velocities in this case, how this varies with Poisson's ratio mean. You know the value of Poisson's ratio varies from 0 to 0.5. So here, and what is given in this figure, the ratio by V by Vs, where V could be the P, or it could be S or R. Naturally, when V equal to S, then it will be the 1, Vs by Vs will be 1, irrespective of the Poisson's ratio. So this line is unity. Now coming to the P wave, where P wave is the velocity is Vc, and this is given, this ratio is given from this relation. When mu equal to 0, this ratio is square root 2. So this value is nothing but square root 2. So this value here is square root 2. Okay. When the Poisson's ratio increases, then this values start increasing. For example, for mu equal to, if you select for mu equal to point, let's say in between, mu equal to 0.25, in that case, what will happen? This ratio will be, this ratio in that case, this ratio will comes out to be root of 2 into 0.75 and divided by 0.5. Okay, so 0.5 divided by 0.5. So that means you have 1.5 divided by 5. So it will go to 1 minus twice 0.25. All right. So you have 0.5. So 1.5. So it will be root 3. So at 0.25, it will be around 1.73. So you could see here it's still less than 2. So this value comes out of here. So up to this 0.3, but as it further increases, especially when the Poisson's ratio is going near to 0.5, then what will happen? It will tend to infinity. So this was the relation between P wave velocity and S wave velocity. As for the relief wave is concerned, there is not much variation in the wave velocity of relief wave Poisson's ratio, and the wave velocity remains more or less same near shear wave velocity. Initially, there is a little difference when the Poisson's ratio is small, this relief wave have about 90% wave velocity with compared to S waves, but then Poisson's ratio increases, it tends to be near to S wave, and both become same. So S wave and relief wave become have the same velocity when u equal to 0.5. Now the last slide here, as we said, there are two types of waves, and one is called body wave, another is surface wave. So in body waves, you have two types again, compression, that is P wave, and shear S wave. All right. Now what you have here in compression waves, how we can define P wave? There are two things. One is called direction of wave propagation, and another is called direction of particle motion. So for P wave, direction of wave propagation and particle motion is same, and that is called compression wave. While for S wave or shear wave, direction of wave propagation is, let's say, in this direction, in the horizontal direction, but particle motion is perpendicular to that. And there could be two perpendiculars. One could be, in vertical directions, and another could be in the horizontal direction. So as a result, your S wave have two components. It could be depending on whether if particle motion is in vertical direction, then it will be SV. Okay, and another component where particle motion is in horizontal direction, then you have horizontal component SS. Now when these body waves comes into contact to the surface, then surface waves are generated. So the relief, so there are two, of course there are others also, but mostly there are two types of surface waves. One is called relief wave and another is love wave. Relief wave is the byproduct of P versus SV wave. Okay, and love wave is the byproduct of coming from SH waves only. Because relief waves are generated from P and SP waves, so it have both horizontal and vertical components. But when we talk about love waves, because it was generated from SH waves only, so it have only in the particle motion only vertical horizontal component only. So this was about wave propagation, and this will be very helpful while dealing with soil interaction and in turn for earthquake resistant design of foundations. Most of the contents of the today's lectures are from following two references. Mostly are from the last one, that is Kramer's book, Geotechnical Earthquake Engineering, and the first one, a book on soil dynamics by Samshir Prakash. So the speaker is thankful to this literature, and that has been explained on SSI. So thank you very much for your kind attention.